Hello, my name is Alexander Popov. I'm glad to tell you about exploiting a Linux kernel vulnerability in Video for Linux subsystem. I'm a kernel developer since 2013 and security researcher at Positive Technologies. The plan of the talk. First, I will describe the vulnerability. I will tell about the bugs, the fixes which I made, and then I will focus on exploitation on x86-64. First, about hitting the race condition to provoke the memory corruption. Then about the control flow hijack for Video for Linux subsystem. Then I will describe the method of bypassing supervisor mode execution and access prevention from the kernel thread context restrictions. And finally, I will tell about privilege escalation payload, show the demo on Ubuntu server, and interesting part, I will tell about possible exploit mitigation. This vulnerability is local privilege escalation in the Linux kernel. The type of the bug is race condition. Everybody may know that race condition is the situation in software when the result of the computation depends on the order of the computations. In, for example, in simultaneous threads. And this vulnerability, CV 2019-18683, refers to three similar bugs in the Vivid driver of Video for Linux subsystem. And several major distributions ship this driver as a kernel module. For example, Ubuntu, Arch Linux, SUSE, and some others. Few words about Video for Linux. It is a collection of drivers and API for video streaming support in the Linux kernel. And the vulnerable driver, the Vivid driver, it is needed for emulating the hardware which is supported by Video for Linux subsystem. And this hardware includes video capture and output and input device, capture and output devices, radio receivers and transmitters, and software-defined radios. This driver is needed for emulating the hardware to test and develop the user space software which interacts with that hardware through Video for Linux subsystem. And this driver brings the attack surface to the system. It turned out that the devices created by the driver is available to normal user, to regular user on Ubuntu. Because Ubuntu applies read-write access list when the user is logged in. Unfortunately, I didn't manage to auto-load the vulnerable module. That's why I did the full disclosure. The timeline. The bugs were introduced in 2014, and around 5 years later, my syslcaller fuzzer with custom modifications hit the bug and gave me the crash. I started the investigation, and a month and a half after that, I had a fully working proof of concept exploit and the fixing patch, which I sent to a security team of the Linux kernel. I decided I chosen to be a good citizen of free software, so I did the responsible disclosure. And 15 minutes later, Linus Torvalds replied and review started. And the next day, I already prepared 2 more versions of the fixing patch. And Linus allowed to do full disclosure because the driver can't be automatically loaded. November 2, I did the full disclosure, but 2 days later, Linus suddenly realized that we had a mistake in the patch. Maybe we can keep details for Q&A, but I sent the next version to the public mailing list since the full disclosure was has already happened, and the CVE was allocated for this issue. November 8, the patch is taken to the to the tree of Video for Linux maintainer and got to the main line. And at the end of November, this patch was applied to stable trees of the Linux kernel. That was the timeline. What was the actual bugs which I found? As I said, I used syscaller with custom modifications, and kernel address sanitizer detected use after free on the linked list manipulations in the vulnerable driver. I started to investigate it, and the reason of this memory corruption was quite far from the memory corruption itself. It turned out that there is the same incorrect approach to locking in those three functions. It is just copied and pasted in three places. And now, let's do that. And now, the puzzle for clever system software developers. So we have process context where we close the file descriptor. During this operation, the mutex is locked. But on closing the file descriptor, the kernel thread, which is doing streaming, should be stopped as well, but this kernel thread uses this mutex as well. What can we do to avoid deadlock on the streaming stop? And that was the wrong answer of the developer in 2014. So it decided to unlock mutex a little while, just to put the kernel thread away. So just you can see the mutex at the gate and the kernel thread as a sheep, which is going to get out when we open the door for a while. It was expectations, but the reality that there are a lot of reader processes which can compete with kernel thread for that mutex and win the race. So unlocking the mutex during streaming stop on closing the file descriptor is a bad idea. What happens? Another reading function can lock the mutex instead of kernel thread and manipulate the queue of the Video for Linux buffers. And that is completely not expected by the Video for Linux subsystem, that the queue is modified during the streaming stop. That is the final patch, which allows to avoid such situations. It is a proper fix. It consists of two parts. First part, I avoid unlocking the mutex on the streaming stop. Just do not unload. Do not unlock. Only ask the thread to stop. And the kernel thread, in kernel thread, I use mutex try lock instead of mutex lock, which immediately fails if it can't lock the mutex. If it fails, it goes to sleep for a while and starts the new iteration of the loop. What happens in case of vulnerability situation? The file descriptor is being closed, and the mutex is locked. Suddenly, the kernel thread wakes up, it tries to lock mutex, fails, and goes to sleep. It happens several times, and then eventually, on closing the file descriptor, the kernel thread stop is called. Next time when kernel thread is woken up, it checks that kernel thread should stop, understand that yes, it's okay to, now it is a moment to exit, and finishes. So it is kind of lockless way how to stop the kernel thread during the streaming stop when they have they need the same resource together. Now let's speak about the exploitation. First part of the exploitation is winning the race, so hitting the race condition. That code I run in several pthreads, which are running simultaneously, and this code hits the race condition. You can see here that that read in one pthread competes with close in another pthread. And when reading is winning and locks the mutex, the linked list is manipulated, and the memory corruption can happen. When a reader wins the race condition and locks the mutex, it adds another VB2 buffer into the VB2 queue. And after the streaming is fully stopped, Video for Linux subsystem cleans up the resources and frees all the buffers in this queue. But the driver is not aware that the buffer which was just added is already freed, and it still has the reference to the freed object. That is use after free, which happens on the next time when streaming is started again. The file descriptor is opened, and we have one read system call for this file descriptor. And here you can see at the kernel address sanitizer report that the object, the vulnerable object, is from kmalloc 1 kilobyte slab cache. Now, exploiting the use after free, how to override the object which was freed. The idea was to use a brilliant approach by Vitaly Nikolenko by setexator powered by user fault fd. What is the main idea? On the first step, Video for Linux allocates the buffer. Then, on streaming stop, it frees the buffer. And after that, from the user space, we call setexator, and kernel allocates the extended attribute in the kernel space. When the size of the extended attribute is the same, is close to VB2 buffer size, allocator gives the same address which was just freed from the similar slab cache. That's why we can put our payload on the freed object and overwrite it. As I said, setexator is powered by user fault fd. It is needed to keep the payload in the kernel space. There is a page fault requested at the end of the area which is allocated in the kernel memory. That's why when the data is copied, the page fault is hit and propagated to the user space. But user space, my handler in the user space does nothing to handle this page fault. That's why the setexator process hangs and keeps the payload in the kernel space forever. Finally, when we have use after free access, the system works with overwritten object with the payload which we put there. And we have the privilege escalation. But it was not so easy to use this approach in my case, because it turned out that the vulnerable VB2 buffer is not the last one which was freed. That's why it was somewhere deeper in the free list, and calling only one kmalloc was not enough to get the same address from the allocator. That's why I really needed to spray. But how to spray when your thread is hangs on the setexator system call? And I used the brute force solution. I just created a pool of threads, dozens of them, and each of them calls setexator, hangs happily, but we have a lot of allocations in various slab caches. Moreover, this approach allows to spread the allocations, distribute them among different CPUs, and have allocations on all slab caches which are per CPU. So, after heap spray is successful, VB2 buffer is overwritten by my payload, and I can use it for privilege escalation. Next step, hijack the control flow in Video for Linux subsystem. I was learning the code of that subsystem for a long time. It was painful. I wanted to find some exploit primitive. My goal was to get arbitrary write primitive, but I didn't manage. But finally, I found the very promising function pointer. Here on this diagram, you can see how objects in Video for Linux are connected together. So there is a VB2 vivid buffer and VB2 buffer structure just at the beginning of the structure. And it has the reference to VB2Q structure, which also has the reference to memops structure. In that memops structure, we have a lot of function pointers, and this excellent vadder function pointer, which is very convenient for exploitation. Moreover, you can see that memprev field is passed to this function pointer when it is called as an argument. So if we override the VB2 buffer, we can control the argument of the function pointer, which will be called. Really nice. So I started the experiment with implementing this idea. And first, I disabled supervisor mode access and execution prevention, kernel page table isolation, those features which can disturb the read to user attack. And I set the pointer to VB2Q to the user space memory, but all the time I got this error, unable to handle page fault. Finally, I found out that this pointer is dereferenced in the context of kernel thread, where user space is not mapped at all. So that brought the trouble for exploitation. I didn't know how to put the payload. Because if the user space is not mapped at all, I should put the payload somewhere in the kernel space, and it should be at the location of address which I know. That was a trouble. But I had a clue. During this experiment, I dropped the kernel changes which I had for deeper fuzzing. And I saw that just before use after free, Video for Linux gives the kernel warning. And this warning contains a lot of interesting information. And moreover, the kernel log, where this warning is printed, is available to regular users on Ubuntu. So maybe it can be useful for exploitation, but I didn't know how to use it. That is the example of the kernel warning. You can see here that there is a code line where warning happened, the contents of the registers, and the call trace. So a lot of information. So I spent some time trying to find a solution, and then asked my friend, Andrei Konovalov, who is a very well-known kernel security researcher, and he presented me with a really good idea to put the payload in the kernel stack and hold it there with the same technique, user fault FD, like in the heap spray by Vitaly Nikolenko. And it was a really nice idea, which helped me a lot. I believe it is a novel method. Let me call it Cyrus method to credit my friend. So I had an insight. I can read the kernel warning, parse it, and extract the stack RSP register and understand the location of the kernel stack. Then next, I can anticipate the future position of the payload in the kernel stack on the next system call. So I have the place with known address in the kernel space where to put my payload. And that was the most pleasant moment of the research, just like Halvor Flake told us today at the keynote. That kind of moment make hacking really joyful. And so I created the exploit orchestra, which did the exploitation. First, I will show the kernel warning with the useful information. Here you can see the RSP register with the address of the kernel stack. And moreover, you can see R11 register. It starts from 8F, which means that that is the location somewhere in the kernel code. And that pointer can be used to bypass kernel address space layout randomization. We can calculate the offset, randomized offset of the kernel text. Now about the exploit orchestra. It consists of 50 pthreads in 5 different roles. There are 2 racer pthreads which compete each other to hit the race condition for later memory corruption. Then I have 44 sprayers which do static stutter to perform the heap spray, powered by user fault FD. Such number, I chosen such number just empirically to make the exploit really stable. So it is the minimal number which I chosen when for the exploit to be really stable and not fail. Then I have 2 pthreads for catching the page fault created by user fault FD. 1 pthread for parsing the kernel log to extract the valuable information from the warning and adapting the payload. Finally, I have the 1 fatality pthread which triggers the privilege escalation. And pthread of different roles synchronize on different sets of pthread barriers. That's how my exploit orchestra looks like. It is me conducting it, pthreads, and this guy with drums. I think he is a fatality pthread which performs the privilege escalation. Now, how the exploit is played. I will describe it in chronological order. First, we have barrier prepare, where all the pthreads prepare before they exploit. 44 sprayers create files in temporary file system for later using in static stutter. And they come to barrier and wait. The kernel message, kernel log parser opens the kernel log, dev k message, and comes to barrier as well. And 2 racers come to the barrier, and when they all together come to the same barrier, the barrier opens and they start to work further. Then we have barrier race. It is only for 2 pthreads. For racers. Racers first sleep for a while to let other pthreads go to the next barrier and sleep. And then 2 racers come to the barrier and after that start to work with Vivid driver, as I described, to hit the race condition. Next barrier is barrier parse. 2 racers, after hitting the race condition, come to this barrier where the kernel message parser is waiting. When racers come, barrier opens and kernel message parser understands, okay, the racing is finished, now I need to parse. It parses the kernel warning, parses the kernel log and finds the RSP and R11 registers, the values of them, and it calculates the addresses for the payload and adapts the payload. Because now, after parsing, we know where the kernel stack is in the memory. Finally, it adapts the payload and comes to the next barrier, barrier case stack. Here, 2 racers are waiting for this pthread, and when they are all together in the pthread, they start they call the adjust timex system call, which puts the payload on the kernel stack. I will tell about this syscall a little bit later. After placing the payload on the kernel stack, in the page fault handler number 2, we catch 2 page faults from the racers. and come to the barrier where sprayers are waiting. Then sprayers understand that it's time to put the payload on the kernel heap and call setXutter, powered by user fault FD, and these pthreads hang. And in the page fault handler number 1, we catch all those page faults, 44 page faults, and understand, okay, now the heap spray is finished. We come to the next pthread, next barrier, barrier fatality, where the fatality pthread is waiting. And fatality pthread understands when the barrier opens that it's time to do the privilege escalation. And that's it. So this method allows to bypass supervisor mode access and execution prevention from the kernel thread context restrictions and bypass kernel address space layout randomization as well on Ubuntu server. Now I want to tell you about the exploit payload. So as I already mentioned, the payload is created in 2 places, in kernel heap by spray pthreads which call setXutter, and in kernel stack by racer pthreads which call adjust timex. Adjust timex is the system call which calls on when kernel handles it. It calls copy from user, from the user space to the kernel stack. There is a structure for the timex structure which is filled by the user space data, and it is large enough to put the payload. The exploit payload consists of 3 parts, which you already seen on the diagram. The first is VB2 buffer, which is in the kernel heap. The second is VB2Q, which is in the kernel stack. And finally, the memops with the function pointer, which is in the kernel stack as well. And this diagram shows my payload, how it is organized. On the left-hand side, you see the kernel heap and VB2 buffer, which is overwritten by our heap spray. This VB2 buffer refers to VB2Q, which is at the known place in the kernel stack. The data to the kernel stack is written to kernel timex structure, but the VB2 buffer refers to the VB2Q, so some type confusion happens because of use after free. The VB2Q refers to memops, and I had to overlap all the structures because I have limited space in the kernel stack. The memops has this vAdder function pointer, which points to stack pivoting gadget. And the argument for this function, for vAdder function, comes from VB2 buffer. And this is address of the ROP chain, which is at the kernel stack as well. So final stack is doing the privilege escalation, and it is some kind of combination of return-oriented programming and jump-oriented programming, so it is ROP and drop. That is the definition of the function where we do the control flow hijack. The argument on x86-64 is passed through via RDI register. And this RDI register is under our control since we control the argument. So there is an excellent gadget which fits these requirements. Push RDI and pop RSP, then return. So our controlled argument goes to stack pointer, and then we can execute our ROP chain. This ROP chain is executed in the kernel thread context, so it is a bit unusual. Usually people just override the credentials of the user space process of the exploit, but here we don't have user space. That's why I had to do it another way. So that is the ROP chain. I will describe it in details. First, we pop the R15 register, and the value which gets to this register is the address of run command function from kernel reboot.c. And the argument for this run command function will be the name of some shell script. So I needed to pass the address of the string as an argument. So next gadget does pop RDI, and the address of the shell command comes to RDI register, which will be the argument of run cmd command. Then I jump to R15, so run cmd command is executed, and the argument of the command is the shell script. Then, after privileges are escalated, I have this do task dead function, which is called the same way. I will describe it why it is needed. But first, I want to show the shell command. It simply drops the password for root. So next time after exploit worked, we can log in under root without giving the password. And the last step with this, the last trick with do task dead is for so-called system fixating. If I let the kernel thread work after the privilege escalation, it provokes some unnecessary kernel crashes, so we need to keep the system working. That's why I decided to just kill this kernel thread, and when do task dead is performed in the kernel thread, it dies, and we have no crashes. System continues to work. Now the demo. Yeah, here I log in as a normal user on the right-hand side and show some information about the system. First, about the distribution, then about the kernel. It is the original Ubuntu kernel. Now I show that supervisor mode access prevention and supervisor mode execution prevention are enabled. You can see it from proc CPU. Yes. Now I show the kernel command line to show that I didn't disable kernel page table isolation or kernel address space layout randomization. And now I show that the vulnerable module is loaded. It is done manually. Yeah, now I show that it is a normal user. I try to log in as root, and it asks for the password. No way. Now let's connect to this virtual machine via SSH and run the exploit. Yeah, very fast. Shell command is run as root. And let's try to log in as root. Yeah, without password. I also want to say that the exploit turned out that exploit is really, really stable. It also never fails. So I'm glad. Now, about possible exploit mitigation. Very interesting part. First of all, recent kernels have this unprivileged user fault FD setting. If we set it to 0, the user fault FD is not available to unprivileged user. So it can disturb the way how the payload was placed in the kernel heap and the kernel stack. Another mitigation is against the info leak through the kernel log. there is a mask restrict syscontrol. If we set it to 1, we need, as I remember, capsysadmin capability to read the kernel log. But, by the way, Ubuntu users, regular users are participants of admin group, and they can read varlog syslog anyway, even if the setting is set to 1. Next is the feature from JR Security, an interesting one, called Pax run kstack. It randomizes the location of the kernel stack on every system call, on each system call. So that makes the exploit guess the future position of the payload on the kernel stack. Next feature, it can break the ROP and drop chain, which I used. It has Pax rep from JR Security as well. Finally, there is, hopefully in future, there will be ARM memory tagging extension support for the Linux kernel, which can kill use after free bug class in general. Now the conclusion. Investigating and fixing this vulnerability, developing the proof of concept exploit, and preparing this talk was a really big deal for me. And I really hope you enjoyed it. Today I will publish a detailed write-up about the exploitation. That's it. Thank you very much.
There is a question. So is the warning that you've used, is it triggered by the same bug, or is it a different bug?
It is triggered by situation when we have buffers in a strange state in the queue of buffers on streaming stop. So it is some generic warning which can happen in different situations as well. But in that case, our driver just triggered this warning because it unexpectedly added the buffer to the queue during the streaming stop.
So it's still possible to trigger it with your fixes applied?
Yes, yes, okay. Because this warning just shows the situation when some driver behaves bad. I want to notice also there was an announcement by ZDI in autumn, as I remember, that there was some vulnerability for Video for Linux subsystem. It was use after free as well. It was reported to ZDI, and Android systems were affected, but it was reported without the proof of concept exploit. I don't know, maybe because of kernel thread restrictions. Anyway, the technique which I showed maybe can be applicable to other bugs in this subsystem.
Any more questions? Doesn't look like it. So thank you. Ah, wait, there's one more.
Thanks for the great talk. Just one question. You've mentioned the custom syscaller implementation or your customizations. Could you tell us more about that?
Yeah, thank you for your question. Syscaller, I would say, fuzzing consists of two parts, the fuzzer itself and the system which you fuzz. So to modify this, your fuzzing, you can change both things. And in my case, I modified the kernel to drop all the unnecessary warnings and information about deadlocks, lockups, and all of that. That allowed the fuzzing process go deeper. Originally, fuzzing would stop on the warning, but I disabled warnings. So my fuzzing hit the use after free bug, which is exploitable. That's why when I disabled my kernel changes for deeper fuzzing, I saw this warning and got an idea how to exploit.
So then, are there now any more questions? Okay. Then thank you very much for the talk.